For more than 200 years, they were basically a ghost story whispered by mathematicians. An object so dense, so powerful, it could literally swallow light. Then, for decades, the very man whose revolutionary equations predicted them refused to believe they were real, calling the whole idea unconvincing. Albert Einstein argued they just couldn't exist in the real world. Black holes were a paradox, a mathematical monster lurking in the depths of space-time. The problem was, how do you prove something exists when its defining feature is that it can't be seen? This is the story of a century-long quest to find the unfindable, and how, through breathtaking ingenuity, we finally succeeded in both hearing and seeing the cosmic monsters that even Einstein thought were impossible. The idea of a black hole is one of the most mind-bending concepts in all of science. It's a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. It's the ultimate point of no return. For decades, this idea lived purely in textbooks and on chalkboards. Physicists saw them as a weird side effect of the math, a curiosity that surely couldn't be a real object in our universe. Proving they were real required more than just a shift in thinking. It demanded a revolution in technology. It would take scientists from suspecting they existed through clever detective work to finally capturing the sound of their cataclysmic collisions and ultimately taking a direct picture of their shadow against the cosmos. This wasn't just about checking a box on a theory. It was about prying open a brand new window onto the universe and getting a look at the most extreme and bizarre objects out there. It's a story of incredible persistence, global teamwork, and the power of human curiosity to solve the deepest secrets of the cosmos. Part 1. The Ghost of a Dark Star. Long before Einstein, before we even knew what galaxies were, the first seed of an idea for a black hole was planted. And it didn't come from a famous physicist at a top university, but from an English country parson and amateur astronomer named John Michell. Back in 1783, Michell ran a fascinating thought experiment. He was working with the physics of his day, Isaac Newton's laws of gravity, and the theory that light was made of tiny particles. Michell figured that, just like a cannonball fired from a planet, these particles of light must be slowed down by the gravity of the star they came from. This led him to a wild question. What if a star was so massive and dense that its escape velocity was faster than the speed of light itself? He did the math and concluded that a star about 500 times the diameter of our sun would trap its own light. The star would be invisible, a dark star. It was a revolutionary idea, but it was so far ahead of its time it was mostly forgotten. Michell even suggested how we might find one. Look for a visible star that seems to be orbiting an invisible partner. A few years later, the brilliant French mathematician Pierre-Simon Laplace independently came up with a nearly identical idea. But with no way to test it, the concept faded away, becoming a historical footnote. It would take a complete reinvention of gravity to bring the monster back out of the darkness. Part 2. Einstein's revolution and his own doubt. The modern story of the black hole kicks off in 1915 with Albert Einstein and his general theory of relativity, which turned our understanding of gravity upside down. Gravity wasn't a force pulling things together anymore. Instead, Einstein showed it was the result of mass and energy warping the very fabric of the universe. A four-dimensional sheet he called space-time. As the physicist John Wheeler later famously said, "Space-time tells matter how to move, matter tells space-time how to curve." A planet orbits the sun not because it's being pulled, but because it's following a straight path through space-time that has been curved by the sun. Einstein's equations were incredibly complex, but just a few months later, a German physicist named Carl Schwarzschild found the first exact solution while serving on the front lines of World War I. His solution described the space-time around a single non-rotating ball of mass, but buried in the math was something deeply weird. If you squeezed enough mass into a tiny enough space, the curvature of space-time would become infinite at the center, a singularity. Surrounding this was a boundary, the point of no return, which we now call the Schwarzschild radius. He had, without realizing it, described a black hole. But this was seen as a flaw in the math not a real possibility. Einstein himself was one of the biggest skeptics. He was so convinced black holes were a fantasy that in 1939, he published a paper arguing they couldn't possibly form in nature. For much of his later career, he believed that as matter collapsed, it would spin faster and faster, preventing it from ever shrinking down to that critical point. The man whose theory predicted black holes spent years arguing they couldn't exist. He just couldn't accept that nature would allow for something so bizarre, a place where the laws of physics break down. Part 3. The Golden Age of Theory. For a few decades, black holes remained on the fringes of physics. But that all changed in the 1960s, in what's now called the Golden Age of black hole theory. A new generation of physicists started taking Einstein's equations more seriously than Einstein himself had. A huge breakthrough came in 1963 from a New Zealand mathematician named Roy Kerr. He found a solution for a rotating black hole. This was a game changer because in the real universe, everything spins. Kerr's solution described a far more realistic object, one that literally drags space-time around with it. Then, the British physicist Roger Penrose proved that once a massive star collapses past a certain point, the formation of a singularity was unavoidable. It wasn't just a mathematical quirk, it was a direct consequence of general relativity. Around the same time, Stephen Hawking showed that the surface area of a black hole's event horizon could never decrease, drawing a strange and powerful link between black holes and the laws of thermodynamics. This work gave black holes a solid theoretical footing, but they still had a terrible name: gravitationally completely collapsed objects. In 1967, the American physicist John Archibald Wheeler finally gave them the catchy name that stuck: black hole. The name captured the public imagination and gave this abstract idea a real identity. The theory was solid, but a huge problem remained. There still wasn't a single shred of proof that they actually existed. Part 4. The hunt for indirect evidence. So, how do you find something you can't see? You look for the chaos it leaves in its wake. In the 1960s and 70s, astronomers started hunting for the telltale effects a massive invisible object would have on its neighbors. Their strategy was the same one John Michel had proposed 200 years earlier. Find a star that's orbiting nothing. In 1964, a rocket detected a powerful source of X-rays in the constellation Cygnus. This source, named Cygnus X-1, was revealed to be a binary system. A massive blue supergiant star was orbiting an unseen companion every 5.6 days. By tracking the visible star, astronomers calculated the mass of its invisible partner. The answer was stunning. The unseen object had to be about 15 to 20 times the mass of our Sun. That was way too heavy to be a neutron star, the other known type of super-dense dead star. The intense X-rays gave another clue. Scientists figured they were coming from an accretion disk, a vast, superheated whirlpool of gas being stripped from the supergiant star. As the gas spiraled toward its doom, friction would heat it to millions of degrees, causing it to glow fiercely in X-rays before it finally slipped past the event horizon and vanished forever. By the early 1970s, the evidence was overwhelming. The massive, invisible object emitting a torrent of X-rays made Cygnus X-1 the first prime suspect for a black hole. It was still indirect evidence, but it was a smoking gun. This became the template for finding more black holes, but the ultimate proof was still decades away. Part 5. The sound of space-time. The first direct, definitive proof that black holes were real didn't come as a picture. It came as a sound, the sound of space-time itself ringing like a bell. Einstein's theory predicts that when truly massive objects accelerate, they create ripples in space-time called gravitational waves. For a century, they were purely theoretical. The ripples are so tiny you need something cataclysmic to detect them, like two black holes smashing into each other. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. Its two giant L-shaped detectors, thousands of miles apart. A laser is split and sent down two 4-kilometer-long arms. When the beams return, they should cancel each other out perfectly. But if a gravitational wave passes by, it stretches one arm and squeezes the other by a distance thousands of times smaller than an atomic nucleus. That tiny disruption is enough to knock the lasers out of sync and create a signal. On September 14, 2015, it happened. Both LIGO detectors picked up a signal. It was a faint chirp that lasted less than a second, but it was unmistakable. Scientists analyzed it and realized exactly what they were hearing: the death spiral of two black holes. About 1.3 billion light-years away, a black hole roughly 36 times the mass of our Sun had merged with one about 29 times the mass of the Sun. In the final fraction of a second, they collided to form a single, more massive black hole of about 63 solar masses. The remaining 3 solar masses worth of material hadn't just vanished. They'd been converted directly into pure energy, in the form of gravitational waves. This was it. It was the first direct detection of gravitational waves and the first unambiguous proof that black holes are real, physical objects that collide throughout the universe. The discovery was so profound, it won a Nobel Prize and opened up a whole new way of doing astronomy. Since then, LIGO and its partners have detected hundreds of these events. We've now gone from not knowing if black holes were real to using their collisions to test the fundamental laws of physics. For instance, in 2021, by reanalyzing that very first signal, scientists were able to observationally confirm Stephen Hawking's area theorem, the idea that a black hole's surface area can never shrink. Then, thanks to detector upgrades, an incredibly clear signal from another merger in 2024 allowed them to verify that same theorem with mind-boggling precision. We are witnessing science unfold in real time. If you're fascinated by these cosmic breakthroughs, make sure to subscribe and hit the notification bell so you don't miss our next deep dive. Part 6. Seeing the unseeable. So we'd heard black holes. But could we ever see one? How do you take a picture of something that absorbs all light? You don't. You take a picture of its shadow. The plan was to capture the silhouette a black hole casts on the glowing, superheated gas swirling around it. The target was the supermassive black hole at the center of the M87 galaxy, 55 million light-years away. Trying to see its event horizon from here is like trying to photograph a donut on the surface of the moon. No single telescope could ever do it. The solution was as brilliant as it was audacious: the Event Horizon Telescope, EHT. The EHT isn't one telescope. It's a global network of radio telescopes all synchronized with atomic clocks and pointed at the same target. By combining their data, you create a virtual telescope the size of planet Earth. In April 2017, this planet-sized eye stared at the heart of M87. After 2 years of processing mountains of data, the team was ready. On April 10, 2019, they unveiled the first ever image of a black hole. The world saw a glowing, fiery ring of light surrounding a perfect circle of pure darkness. It was the shadow of the beast. The bright ring was light from superheated gas, its path bent into a circle by the black hole's immense gravity. The dark patch in the middle was the event horizon, the point of no escape. The image looked almost exactly like Einstein's theories predicted, confirming a century of work. We were looking at the edge of reality, a visual confirmation of an object with an estimated mass of 6.5 billion times that of our Sun. We had finally seen the unseeable. Part 7. Our own cosmic monster. The M87 image was a triumph, but the EHT had another, more personal target: the supermassive black hole at the center of our own galaxy, the Milky Way. Its name is Sagittarius A, or Sur A for short. Esquire A presented its own unique challenges. It's much closer, only 27,000 light-years away, but it's also much smaller, about 4 million times the mass of our Sun compared to M87's 6.5 billion. Because it's smaller, the gas around it whips around in minutes, not days. Trying to photograph it was like trying to get a clear shot of a spinning top. Despite the difficulties, in May 2022, the EHT collaboration released the first image of Sagittarius A. It looked remarkably similar to M87, a fuzzy ring of light surrounding a dark, central shadow. This suggested that no matter the size, the fundamental physics of a black hole is the same. More recent observations have revealed even more, showing strong, organized magnetic fields spiraling around the edge of the event horizon. These fields are thought to be key to how black holes feed and sometimes launch powerful jets of material back out into space. By studying the monster in our own galactic backyard, we're getting an unprecedented look at the engine at the heart of the Milky Way. Conclusion: the story of proving black holes exist is one of the greatest detective stories in science. It started as a strange idea about a dark star in the 18th century, so odd it was mostly ignored. It was reborn over a century later as a mathematical ghost in Einstein's equations. A prediction so bizarre that even Einstein himself fought against it. For decades, theorists insisted these objects weren't just quirks in the math, but an inevitable part of our universe. Then came the astronomers, the hunters who looked for their cosmic footprints and found a smoking gun in the X-rays of Cygnus X-1. Finally, in our lifetime, came the definitive proof. First we heard them, as LIGO caught the faint chirp of two black holes merging a billion light-years away. Then we saw them, as the Event Horizon Telescope gave us that breathtaking image of a shadow at the heart of a distant galaxy. From a mind-bending prediction to a tangible, visible, and audible reality, the journey to find black holes is a testament to what we can figure out when we refuse to believe something is impossible. The ghost has finally been found, and we're just beginning to understand what it has to tell us.